Hi everyone, my name is Scott, and this presentation is for the final project of CogSci 118B, Introduction to Unsupervised Machine Learning. For this final project, I chose the MNIST for Fashion dataset, which contains several thousands of grayscale image of the fashion data, including t-shirts, sandals, and sneaker etc. So let's get started. Let's see what we can do with. Then once we got the data, let's do some exploratory data analysis on it. This data has the training set has 10 labels in total, and each labels has 6,000 image associated with them. And let's plot the first image of each categories. Why not? And we can see that the image is all about the shirts and the clothing and the fashions um, that we're wearing. And then let's calculate the mean image of every image that we have. So the mean image does not show tons of underlying structures, and this is expected because the fashion data does not have underlying general overarching structures underlying it. Unlike the face dataset we worked before, the face dataset aligns the eyes, the nose, and the mouth together. So when we calculate the mean image of the face data, we will see a mean face. But the mean image of the fashion data does not show a prominent structures. How about we calculate the mean image of each category? This is the mean image of each category, and we can see that although kind of varies, it's kind of vague, but we can vaguely recognize that there is some underlying structure of each categories. So we can say that this data is structural, and it can be clustered. So that's for the exploratory data analysis. Then let's do some unsupervised machine learning. So first of all, we use principal component analysis to do the embeddings and dimensionality reductions. And it is worth mentioning that PCA is a lossy compression method. If we chunked out, if we only choose to save a certain amount of principal components to compress the data, we eventually lost some data, and that amount of variance is not captured. So let's initialize some PCAs. We first of all import from the scikit-learn decomposition, import PCA, and fit transform our image. And this is the embeddings of the PCAs with the top two eigenvectors. We can see that in the plot, there are some underlying structure between each image, and but each image are kind of mingled together. And if we want to do classification on these embeddings, it's not ideal because while we can see that there is a stripe, clear stripes between them, when we apply the KNN, K nearest neighbors method, it will not separate those classes good. So let's further dive into the PCA. Let's plot out the eigen clothings. Why not? So we could see that in here, the principal component of the MNIST data, MNIST for fashion data, is kind of like encoding for the first principal component encodes whether this is a shirt. The second principal component encodes whether it is a trouser, and it's kind of like that. The reason why it's capturing using that method is along those axes, this is the direction with the highest variance. However, when using PCA, there are some shortcomings from the previous graph that we can see that there is several classes of data point are mingled around together. This is kind of bad for us if we want to classify a certain category of image. Therefore, a new clustering method called t-SNE, which stands for T-distributed stochastic neighboring embeddings, will help us to do the trick. So t-SNE is an iterated process of manifold learning, and the t-SNEs can be summarized by the following steps. First of all, a probability distribution over pairs of high-dimensional data are constructed, and such that the data points which are closer in higher dimension will have a higher probability of placing closer in the lower dimension space. And then based on the probability distribution created in the first stage, t-SNE mapped the point from the higher dimension to the lower dimension that minimized the KL divergence. And this is an iterative process, so it goes back to the first one until it is finished. So because t-SNE is constantly calculating the distance in the higher dimensional plane, we want to shrink our data so that we make the computation efficient. So this graph shows how many variants of each principal component will capture. So I set a threshold for 90% of the variance, means that I want the amount of principal component that capture 90% of the variance. In the graph, the red dotted line shows that 83 principal components will capture that amount of variance for me. So this embedding first is indexing out the amount of principal component I need, and then do the t-SNE embeddings for me. So let's have a comparison between t-SNE and PCA clustering. So from the left, we have a PCA embeddings, of which is we can see there's a structure between class, but within the class, they are kind of mingled together. So for example, the first cluster here contains the purple dot, the orange dot, and the yellow dot. However, in contrast, in the t-SNE embeddings, we can see that there are clearly structural between the pink, the orange, and the blue data dot. Because of the extra variance that t-SNE is capturing, we can see that t-SNE has a more clear defined cluster shape compared with the PCA embeddings. And if we want to find the underlying structure of the t-SNE embedding, we could use the watershed segmentation. And because of the time constraint, I won't get into it. Basically, it's fitting a Gaussian kernel of the density, and you could imagine it as a water flows through the plane and just segmentate different planes. And thank you for listening, and hope you're enjoying my presentation. Thank you.